The paper to be presented is entitled Hysteretic Behavior of Q275 and Q690 Structural Steel Materials. The research work is supported by the Hong Kong Constructional Metal Structures Association, formed as part of our industrial-led research program at the Hong Kong Polytechnic University on effective uses of high-strength steel materials in building construction. The research findings of these studies will be contributed to the material requirements for design of steel structures. This paper aims to establish a standardized testing method for low-cycle high-strength cyclic tests. Through a standardized testing method, we can study and compare the hysteretic behavior of different steel materials. Hence, it is essential to propose failure criterion of a standardized test. It is generally recognized that earthquake is the perceptible shaking of the surface of the Earth, resulting from the sudden released energy through the crust movement of the Earth that creates seismic waves. Building structures should be designed and built to the seismic requirement, according to the seismicity level of their location. Conventionally, the seismic requirements for structural steels are mainly relied on these ductility requirements, which has been adopted by the industry for a long time for normal-grade structural steels. However, lack of information can be found in the literature supporting these quantities. In reality, steel materials should be designed to resist cyclic loading due to seismic actions. The seismic requirements for materials should refer to their hysteretic behavior rather than their ductility merely. Recent development of seismic resistance design proposes different requirements on the hysteretic behavior of structural steel materials, which are determined with low-cycle high-strength tests. The current research studies on cyclic tests are mainly contributed by the fracture mechanics, fatigue engineering, aerodynamics, and mechanical engineering, and the current standardized cyclic test methods were also established for those applications. Hence, different testing details could be found in the literature due to different applications. The key differences of the cyclic tests were found to be low particles, geometry of test specimen, and the strain rate or loading rate of the tests. Therefore, it is highly desirable to establish a standardized testing method to define a generic loading particle, a test specimen of suitable geometry, and an appropriate loading rate for characterization of steel materials in seismic engineering. As proposed by FEMA 461, the loading particles reflect the median values of the normalized cyclic amplitudes. This is in good agreement with Eurocode 8 Part 1, which allows that the average value of all analysis, if the response is obtained from more than 7 different accelerometers. In order to prevent from buckling, a funnel-shaped test specimen is adopted according to BS 3518 and GBT 15248. After considering recommendations given in FEMA 461 and displacement responses of single degree of freedom systems, the acceptable loading rate is proposed to range from 0.01 Hz to 10 Hz. A triangular cyclic shape is considered to be suitable. Now I would like to present the recent experimental results on the low-cycle high-strength tests for both Q275 and Q690 steel materials. The experimental investigation consists of 6 low-cycle high-strength cyclic tests and a total of 4 reference tensile tests, which were carried out to the proposed standardized test method and BSEN ISO 6892 Part 1 respectively. The picture shows the typical test setup of the cyclic test carried out in our laboratory in the Hong Kong Polytechnic University. Hence, a total of 6 backbone curves were obtained to assess the hysteretic behavior of Q275 steel materials and that of Q690 steel materials. The backbone curves are defined as the traced line of the largest stresses of each low cycle until the completion of tests. We have introduced 2 parameters to identify the failure criteria. One is strength enhancement factor. This is a ratio of the strength at the strain demand and the 0.2% strength under cyclic loads. The other one is ductility reduction factor. This is a ratio of the strain at fracture after cyclic test and the strain at fracture of the reference tensile test. The test results are summarized in the following table. It is noted that for both Q275 and Q690 steel materials, the 0.2% proof strength obtained from the cyclic tests is significantly larger than those obtained by reference tensile tests. A kinematic factor is defined to indicate the kinematic effects induced throughout the cyclic tests. The total elongations of Q275 and Q690 steel materials at fracture are found to be 16% and 10.8% respectively. The total elongations after cyclic actions are found to be reduced to about 67% for both Q275 and Q690 steel materials, when compared with those values obtained from the reference tensile tests. It is also found that the hysteretic behavior of both Q275 and Q690 steel materials is considered to have favorable strength enhancement after cyclic tests at a strain demand of 2.5%, since all strength enhancement factors are found to be larger than 1.0. In this study of hysteretic behavior of structural steel materials, comprehensive review on low-cycle high-strength cyclic tests adopted by various disciplines of engineering is described. A standardized low-cycle high-strength cyclic testing method suitable to characterize structural steel materials in seismic resistant design is proposed. This will facilitate assessment on the hysteretic behavior of various types of structural steel materials, and engineers can make an informed choice on these steel materials during advanced performance-based seismic engineering design.